In this video, we're going to take a closer look at RLC circuits because their behavior is so important to matching networks. One easy place to start analyzing the behavior of a series RLC circuit is its impedance. I've written the input impedance of an RLC network, ZRLC, here. We can tell just looking at it that there's some frequency where ZRLC is purely real, so we can start defining some interesting properties. First, we call the frequency where the imaginary part is 0 omega naught, the natural frequency. We'll also call this the resonant frequency, even though that's a slight misnomer in circuits with a lot of loss. We can check that I calculated omega naught correctly by calculating omega naught times L and 1 over omega naught times C, which are both the square root of L over C, so they subtract to 0. This quantity shows up a lot, so it's often referred to confusingly as the characteristic impedance of an RLC circuit. We're not going to use that term much more in this class, but I've given it a different symbol than the characteristic impedance of a transmission line just in case. Finally, note that the reactance changes sign above and below resonance, so the system looks a little inductive above resonance and a little capacitive below resonance, as the omega L term or 1 over omega C term dominates the sum. We can calculate the magnitude of the impedance in this network, and we can see that the magnitude is minimized at resonance. So we're going to get the most current delivered to our resistor at resonance. We also know from our first set of equations that the current delivered at resonance is purely real, so it will be in phase with the voltage V. This is because the reactive components have a net zero impedance at resonance, so it's common to say series LC tanks ring short because of the cancellation between the inductor and the capacitor. They add to zero impedance and look like a wire. That calculation is great, but it overlooks some crazy things that are happening in the inductor and capacitor at the same time. We know the current at resonance is going to be given by V over R because the total reactance is 0, but when we substitute that current into the expressions for inductor voltage, we see it's 90 degrees out of phase with the resistor voltage and scaled by a factor of the characteristic impedance divided by the resistance. We're going to call that factor Q, or the quality factor. Q is often much greater than 1, so a 1 volt peak-to-peak signal on the resistor can easily cause 10 volts peak-to-peak on the capacitor, so be mindful of voltage and power handling ratings when you're building resonant circuits. It might seem crazy that we have this big voltage running around in our system, but it doesn't appear over our resistor at all. However, if we calculate the capacitor voltage, we find that it's also amplified by Q and shifted by negative 90 degrees. The inductor and the capacitor voltages exactly cancel out, leaving only the real resistor voltage. Our motivating question when asking about quality factor was finding the bandwidth of a series RLC circuit. That quantity is very tightly related to the quality factor of the system, such that high-quality systems have low bandwidth and low-quality systems have high bandwidth. We can see that by finding the voltage across the resistor using a voltage divider as shown here. If we find the magnitude of the voltage, we can observe that it will be reduced by the square root of 2 when plus or minus the reactance is equal to the resistance, as shown here. This second term becomes equal to the first. Reducing the voltage by the square root of 2 halves the power dissipated in the resistor, which is how we get the traditional minus 3 dB definition of bandwidth. That relation gives rise to a quadratic equation, and I've shown the equation and its solution here. Converting from L's and C's to omega naughts and Q's requires a little bit of creative substitution, as shown, but after some aggressive factoring you get a nice relationship that shows the upper and lower 3 dB frequencies, which is this one here. Those two frequencies are fully specify the bandwidth of the RLC circuit, and they are a Q-dependent fraction of the natural frequency. We find our bandwidth by looking at the difference between the upper and lower 3 dB points, which we call delta omega. In this line, we divide the result on the previous line by omega naught and subtract the upper 3 dB frequency from the lower one. So this is the upper frequency and this is the lower frequency. The last assumption we make is that Q is kind of big, which allows us to neglect these two terms for a clear relation. Our bandwidth as a fraction of the natural frequency is 1 over Q. This type of description of bandwidth is often called the fractional bandwidth. Because our bandwidth is related to Q, you might expect a handy time domain interpretation of Q as well. Q affects rise time in some interesting ways. My favorite stupid Q trick is that you can get an approximate measure of Q by counting how many cycles an RLC circuit rings through before it settles to about 5%. You can see this because the envelope of the decaying exponential in a step response is set by the natural frequency in Q, so this decaying quantity. If you set the time t to be 1 period of 2 pi over omega naught, the argument of the exponential becomes minus pi over q. That's handy, but not nearly as handy as remembering that after q cycles, the envelope will have shrunk to e to the minus pi, which is about 4% of the initial step. Humans can usually eyeball that value pretty well, so you can pick q off of second-order transient responses just by counting peaks. This slide has some example transient responses for you to practice with. And if we were to do so now, we could say for the q equals 5 system, we see 1, 2, 3, 4, 5 peaks before it gets kind of small. Finally, we've been focusing on RLC circuits in this video, on series RLC circuits in this video, but parallel RLC circuits are a natural dual to them. You find the input admittance instead of the input impedance to define resonance, and you drive them with a current source instead of a voltage source, because a voltage source would just see 3 fairly boring independent branches, right? You'd just get V across all of these circuits. The natural frequency is calculated the same way as a series RLC circuit, but the quality factor is the inverse. So it's R over the characteristic impedance instead of characteristic impedance over R. We'll talk about an easy way to remember the quality factor of this in a series RLC circuit soon, but there's a handy mnemonic for remembering where the R goes on top or bottom. Like in the series RLC case, the L and C branches of this circuit experience very high stresses at resonance. In this case, the currents in the L and C branches are Q times higher than the R branch, but they're in opposite directions, so they sum to 0 and the resistor doesn't perceive the big currents running around it in the system. These big currents suggest an interesting piece of physics. The impedance in the L and C branches has been reduced by a factor of Q compared to the resistor, which is similar behavior to the quarter wave transmission lines or various types of transformers. All of those circuits appear to reduce impedance. We're going to describe these impedance transformations soon using a mathematical construct called the series to parallel transformation, and we're going to make use of that transformation to build matching networks for systems where Rn is not equal to 1. Stay tuned! So, in summary, impedance is real at resonance. L and C experience large stresses, voltage in series or currents in parallel resonance. The natural frequency and the quality factor describe second-order systems, and I've included formulas for them down here. And Q sets the bandwidth of a second-order bandpass. So you can find Q as delta omega, so delta omega over omega is given by 1 over Q.